All right, welcome everyone to another video. This one is dedicated to solving a few practice problems from the Otto and diesel cycles. The lecture video for Otto and diesel cycles is listed down in the description below. If you need a refresher on the topic, make sure to check the link out. Let's start with the first problem. We have an ideal Otto cycle with a compression ratio of 8. Intake air is at 95 kilopascals and 27 degrees Celsius. And the problem specifically says that 750 kilojoules per kilogram of heat is added to the air mixture in the cycle during the combustion process, which is our heat addition process. Working with constant cold air properties, we are tasked to find the pressure and temperature after the combustion, the network output, the thermal efficiency, and the mean effective pressure for the cycle. So for the problems of this sort, I would always suggest to start with a very basic PV diagram, just so that we know what's going on, right? So this is the V. This can be specific volume or total volume. It doesn't really matter. I'm going to go with specific volume here. And the pressure is top here in kilopascals, let's say. And so that we know that for an Otto cycle, we are looking at something that looks like this, right? This is 0.1, this is 0.2, and isentropic compression. Then we have a constant volume heat addition. We have an isentropic expansion. And finally, a constant volume heat rejection. Very good. So here, what we know is that the compression ratio, we usually show it with R, is 8. Keep in mind that compression ratio is actually volume of 1, state 1, to volume of state 2. Keep in mind that volume 1 is equal to volume 4, and volume 2 is equal to volume 3. So depending on the problem, some of these, all of these, or none of these may be useful, but it is good to have them here just in case. Also at the intake, I'm going to show it with 0.1. We are looking at P1 is 95 kilopascals and T1 is 27 degrees Celsius. Please take note that for the discussions of Otto and diesel cycle, the temperatures that you put in the different equations that we have, they must be in Kelvin. Or if you're using the British units, they have to be in Rankine. So this is 27 degrees Celsius. I have to add 273 to it to convert it to 300 Kelvin. Very good. Okay. Now the problem says use the cold air, where is it? The cold air properties. That is a, that is a cue for you to use the following information as given. Cp, the specific heat of air at constant pressure, is 1.005 kilojoules per kilogram Kelvin. Cv, the specific heat at constant volume, we may not have to use it, but it is part of cold air properties. So it is 0.718 kilojoules per kilogram Kelvin. In some textbooks, we use K to refer to specific heat ratios. In some textbooks, we use Greek letter gamma. It doesn't matter, whatever you're using. It is going to be the ratio of Cp to Cv, which for us is 1.4. And finally, the gas constant, R, for air, a cold air standard value, is 0.287 kilojoules per kilogram Kelvin. So this is the cold air properties. Now, we are going to assume that air properties are independent of temperature. which is not quite an accurate assumption, but as we discussed in the lecture, this assumption greatly helps us with simplification of our analysis. All right, so let's get to work. The first bit of the problem, part A, asks us to find the pressure and temperature after the combustion. Very good. So let's start with the temperature. As I mentioned earlier, process 2 to 3 is where the heat is added to your cycle. So one can make the argument that Q in is equal to, keep in mind that this is a constant volume process. So it's going to be CV T3 minus T2. So for the constant volume heat addition, this is your first law of thermodynamics. Q is CV delta T, T3 minus T2. The temperature after the combustion is T3, and we are looking for it, right? Okay, so in this equation, what do I know? Q is explicitly given. The problem says 750 kilojoules per kilogram. So Q I know. CV from the cold air properties, I know. T3 is the one I'm looking for. And T2, what about T2? So from the first glance, you may argue that, hey, I don't know anything about T2. And that is correct. However, process from 1 to 2 is an isentropic compression. For an isentropic compression, I have equations that relate the temperature and the specific volumes. So let's use them. I can say T2 over T1 is actually specific volume 1 over specific volume 2 raised to K minus 1, K being specific heat ratio. So T2, I'm looking for. T1, the problem says it's 300 Kelvin. The problem actually said 27 degrees Celsius, but we knew that we have to convert it to Kelvin. So T2 over 300 is equal to. Now, what is V1 over V2? See, V1 is the maximum volume of our cycle, whereas V2 is the minimum volume of our cycle, right? And we know that this R is the ratio of V1 max to V2 mean. So we already know what V1 to V2 is. It is going to be 8. So 8 raised to K 1.4 minus 1. Essentially 8 raised to 0.4. Now, if you use a calculator, plug in the numbers here, you get that T2 is 689.22 Kelvin. So, as easy as that, I was able to calculate T2. Now that T2 is found, I can plug it here and find the missing T3. So let's do it. I can say T3 is 750 kilojoules per kilogram Q in divided by CV, which is 0.718, plus 689.22. Plug everything in your calculator and you get that T3 is 1733.79 Kelvin. So T3 is done. Next, we are tasked to find P3, I believe, right? There are many ways of tackling this problem, specifically to find the pressure, because it is a closed system And it is going through 4 processes that are all very well known, 2 isentropic processes and 2 constant volume processes. So because you know the relation between every process, you can easily manipulate the numbers that you have to find P3. However, I'm going to follow a kind of interesting way of finding P3. I'm not claiming it to be the easiest way of finding P3, but it is actually very interesting. And the reason that I'm doing this is we are going to need some of the findings in this method later on for part D of the problem. So without further ado, let's go. I am going to say, hey, at the end of the day, everything in this cycle follows the ideal gas equation. So with that said, I can say P1 specific volume 1 is equal to RT1. That's the ideal gas equation. Now, in this equation, I know P1, it is 95 kilopascals. I do not know specific volume 1. I know that R, gas constant, is 0.287, and I know that T1 is 300. From this, you get that the specific volume 1 is 0.91 meters cubed per kilogram. So the maximum specific volume of our cycle is 0.91. Now that I know this, remember that the compression ratio is V1 over V2. Also, please remember that V2 is equal to V3 because 2 to 3 is a constant volume process. I'm going to scroll up so that you can see that V2 and V3 are the same because 2 to 3 is a constant volume process. So now I can claim that R is actually specific volume 1 over specific volume 3. This helps me to find specific volume 3. It is going to be 0.91 divided by 8. Again, using a calculator, you see that specific volume 3 is going to be 0.11375 meters cubed per kilogram. Again, ideal gas equation is true for every state of this cycle. So now that I know V3, I can claim P3 V3 is equal to RT3. Ideal gas equation again, right? Now this time, P3 is what I'm gunning for. V3 is 0.11375. R is again 0.287. And T3, we calculated above, it's 1733.79. Using a calculator, you can easily find that P3 is 4374.49 kilopascal, or about 4.37 megapascals. Now, before we go any further, I want to draw your attention to the units I'm using. Please take note that the pressure in ideal gas is kilopascals only if R is in kilojoules per kilogram Kelvin. If the R that you're using, the gas constant that you're using, is in joules per kilogram, then the pressure that you put here, or the pressure that you find from this equation, is going to be in pascals, not kilopascals. So this is a very easy mistake to make, a very common mistake to make. So I just wanted to draw your attention to the units. Always double check the units that you're working with. So for part B, we're tasked to find the work output. Again, there are multiple ways of trying to find the work output, but I think maybe the easiest way of doing it is doing part C first and then come back to part B. Let me show you. So part C only asks for the efficiency. Now, we know that for a ideal Otto cycle, the efficiency of the cycle follows this simple equation, 1 minus 1 over R raised to K minus 1. For the numbers that we have, we are looking at 1 minus 1 over 8 raised to 1.4 minus 1, which is essentially 1 minus 1 over 8 raised to 0.4. Using a calculator, one can easily see that the efficiency is 0.565, or the efficiency is 56.5%. Okay, now that we have the efficiency, it is easier to use the efficiency to find the work output. Let me show you. Efficiency, by definition, is the work output, the network output, over the Q input. So I can say, hey, 0.565 is equal to the amount of network I'm looking for over 750 kilojoules per kilogram worth of heat added to this cycle. Using a calculator, we can easily find that the network is 423.75 kilojoules per kilogram. All right. Again, I want to emphasize that there are other ways of calculating the W net prior to calculating the efficiency, but I think this is the easiest way of doing it. For part D, we are tasked to find the mean effective pressure. Now, the mean effective pressure, sometimes shown by MEP, sometimes shown by PMEFF, is defined as the work output, well, the network output, over the displaced volume. It's a pseudo pressure that helps us engineers to gauge the output of an engine without knowing all the details of the compression ratio, the highest temperature, the lowest temperature. Without knowing all of that, this pseudo pressure, MEP or PMEFF, just gives us what we want to know. As long as you know the mean effective pressure and the displaced volume of your engine, you know how much power you can get out of this engine. All right, so if you want to calculate it, as the problem asks, what we want to do is follow the equation, simple as that. The W net, we just calculated it, is 423.75 kilojoules per kilogram. And the displacement volume is actually the difference between volume max, which is V1, and volume min, which is V2. And a few minutes ago, I told you that I'm taking this longer route to answer part A because I needed some of the numbers. That's what I meant when I said that. I need V1 and V2, which is equal to V3. And now I can plug them here. So 0.91 minus 0.11375. Use a calculator, and you get 532. And you use a calculator, and you get 532.18 kilopascals. Okay, so let's take a look at our second problem. We, again, are dealing with an Otto cycle. The compression ratio is, again, 8. The intake air, we know its pressure, we know its temperature, and in this problem, we know the actual volume of the intake air into the cylinder. It is 0.004 meters cubed, which is roughly 4 liters. Not roughly, exactly 4 liters, as a matter of fact. The maximum cycle temperature is given to us. We are tasked to find, for each repetition of the cycle, the heat rejection and the network production, as well as the efficiency of the cycle. So again, just like before, I would always suggest to draw a simple drawing of the cycle that you're dealing with. This is not only for Otto and diesel cycles, but for any cycle-based problem, because it will give you a general idea of what you're dealing with. So this is 1 intake, 2, 3, and 4. 2 isentropic processes and 2 constant volume processes. So this is my specific volume and this is my pressure. All right, now the problem says that the maximum cycle temperature is 1127. Maximum temperature for the cycle is good, but I can't see it on a PV diagram. So I'm adding a TS diagram as well. So this is T and this is S. You are looking at a isentropic process from 1 to 2, a constant volume process from 2 to 3, a isentropic process from 3 to 4, and a constant volume process from 4 to 1. Now, when you look at the process this way, it is easy to see that T3 is the maximum temperature. So now we know that T3 is 1127 degrees Celsius. Now, please keep in mind the temperatures need to be in Kelvin. So I'm going to add 273 to it to get a grand total of 1,400 Kelvin. Let's list the rest of the problem information. So our compression ratio is 8, very good. The intake information, P1 is 90 kilopascals, very good. T1 is 27 degrees Celsius. Same story as before, change it to Kelvin, 300 Kelvin. And volume 1, 4 liters, also known. I'm going to take the easy route and start with calculating the efficiency first. I know that it's the last thing that the problem is asking, but it usually is the easiest of the bunch to calculate. So efficiency 1 minus 1 over R raised to K minus 1. For us, it means 1 minus 1 over 8 raised to 0.4. Our efficiency is 0.54. So the efficiency is out of the way. We got that first. Now we can focus on the rest of the problem. We are tasked to find the network production and heat rejection. Take note that in Otto cycle, process 4 to 1 is the heat rejection, and process 2 to 3 is the heat addition. So again, there are multiple ways of doing it. You can focus on heat rejection, or you can use the heat addition and then combine that with efficiency to find the network. Your hands are open. You can tackle the problem however you want. I am going to tackle it from a heat addition perspective first. So heat addition, showing it with Qn, is CV T3 minus T2. In this form, Qn is not known. CV, we know it. It's a constant. T3, the problem gave it to us. T2, I have no idea. Now, the good thing is that just like before, we can relate T2 and T1 through an isentropic relation. So let's do it. T2 over T1 is equal to V1 over V2 raised to K minus 1 T2 over T1 is going to be now V1 over V2 is the compression ratio, right? So the compression ratio is going to be 7 raised to 0.4. T1 we know is 300 Kelvin. And so you get that T2 is 653.37 degrees Kelvin. We can now plug this information in our Qin equation to find the heat addition, right? So Qin is going to be 0.718, that is CV. T3 is 1400 minus T2, 653.37. Plug in these numbers in the calculator and you get that Qin is 536.08 kilojoules per kilogram. Now, obviously, this is not something that the problem was asking, but bear with me. I'm going to show you how this is going to work. The problem was asking for the total heat rejection and net work output. It was not asking for the rate of work per unit mass. What we have here is kilojoules per kilogram. So per unit mass of air in our cycle, this amount of heat is added. But can we find the mass of air in our system? The answer is actually yes, we can find it. Let me show you. To find the air mass. It is actually a very simple process. Remember that ideal gas equation is true. For any stage of the cycle, ideal gas equation is true. Also remember that the ideal gas equation comes in different forms. So the one that I used in the previous problem was PV equals RT. In this equation, V is a specific volume. However, we have a variant with the total volume. P total volume is equal to the mass of your gas times RT. This form is the one that we are going to use here in this problem. So at point 1, I know that the pressure is 90 kilopascals. I know that the total volume is 0.004 meters cubed. I don't know the mass. I know that R is 0.287. And I know that the temperature T1 is 300 Kelvin. Playing with these numbers, you get that M, or the mass of air in your system, is 0.0042 kilograms. About 4 grams of air is in this cycle. Remember from before, there is a relation between capital Q and small letter q. Capital letter Q is mass of your system times small letter q. So as easy as that, capital Q in is 0.0042 times the number we have on top in the box, 536.08, for a grand total of 2.251 kilojoules. So I found the Q in, but again, this is not something that the problem was asking. The problem was asking the rejection and the net work. So what I'm going to do is use the thermal efficiency definition. We are looking at the net output over the Q input. Now from before, I know that the efficiency is 0.54. Net work is what we are looking for, and Q input is 2.251. And so your net work out of this cycle is 1.21 kilojoules. Finally, to answer the last part of the question, the heat rejection part, from first law of thermodynamics for this cycle, we know that the net work is equal to Q in minus Q out representing the heat rejected. So Q out is going to be 2.251 minus 1.21, and the rejected heat is 1.04 kilojoules. Okay, so for the third problem, we are again looking at a gasoline engine, which is running on an Otto cycle, right? This gasoline engine is running at 1800 RPM with a total displacement volume of 3 liters. Compression ratio is also given. The intake temperature and pressure are also provided. The mean effective pressure, the pseudo pressure that we discussed earlier, is also given. We are tasked to find the cycle efficiency and the power output. Let's start with some of the things that are more interesting in the wording of the problem. Displacement volume. Now, from the lecture video, we know that the displacement volume is the max volume, or the top dead center, the bottom dead center volume, minus the minimum volume, which is the top dead center volume. Now, this Vmax minus Vmin is 3 liters. 3 liters, for those of you who are curious, for the unit conversion, every 1 liter is 1,000th of a meters cube. So this is about exactly, as a matter of fact, 0.003 meters cube. The compression ratio is maximum volume over minimum volume. And this is 10. Now, if we take a look at our trusty PV diagram for a Otto cycle, we see this familiar plot. This is point 1, 2, 3, and 4. Obviously, we put arrows on the processes so we know what's going on. By just looking at this, you realize that V1 is the maximum volume, V2 is the minimum volume. Now, the mean effective pressure, by definition, is the work output over the displacement volume. I can go ahead and say, hey, the problem says this is 600 kilopascals. This will be the W net of 1 cycle over the displacement volume, which is 3 liters. Keep in mind that you have to have unit consistency. Liter is not a unit that we use in our equations. Meters cube is. So you have to convert this to meters cube first. So now we get that the net output work for 1 repetition of the cycle is 1.8 kilojoules. But this is for 1 repetition. The problem is actually asking for power output, not work output. The unit here is kilojoules. We are looking for power output. Power has a unit of kilowatts. To find power, we need to know how much work is generated per second in this cycle. Now, how do we do that? I can say that, hey, 1 cycle generates 1.8 kilojoules. How many cycles does its engine go through in any given minute, let's say? Now, I say per minute because I know the RPM of this engine. So 1800 RPM means that the crankshaft of this engine goes through 1800 revolutions per minute. If I know how many revolutions it goes through over a minute, I can easily calculate how many it goes through per second, right? So I can say, hey, 1800 RPM, I'm going to write it as rev per minute. And then I'm going to multiply this by minute over 60 seconds. If I do this, you can easily see that I can change the RPM to RPS, revolutions per second. Very good. So 1800 divided by 60 is the number of revolutions per second. So if, theoretically speaking, I multiply this by the work output for one cycle, which is 1.8, then I should be good, right? Now, from the lecture, you may remember that there is a line here from state 0 to state 1, and you have two arrows in the opposite directions on this line, representing two different processes, from 0 to 1 and from 1 to 0. Now, in the lecture, we talked about how these two processes, 0 to 1 and 1 to 0, do not affect the work output of the cycle, and as such, we usually don't draw them. However, fully understand how the engine works, I'm adding the 0 to 1 and 1, 0 here, so we can see that during a full cycle, the piston has to go through one expansion, one compression, one expansion, and yet another compression. So 2 expansion and 2 compression, meaning that every one cycle requires 2 revolutions of the crankshaft. So when the engine is running at 1800 revolutions per minute, the system goes through 900 cycles, because every 2 revolutions is one cycle. Now, that is the final correction to our equation here. You have to divide the RPM by 2. Now, when you do this and you plug in the numbers, you get that this 60 makes this 30, right? And the 2 makes this 0.9, and you are looking at 27 kilowatts. So the power output of this engine running at 1800 RPM is 27 kilowatts. Okay, we are not done yet. The question also asks for the efficiency, but you should be very familiar with how to find the efficiency of the Otto cycle. It is 1 minus 1 over R raised to K minus 1. For us, it translates to 1 minus 1 over 10 raised to 0.4. Plug in everything into your calculator, and you get that the efficiency is 60.19%. So this problem, as you can see, it only required 4 or 5 lines of calculation. It is very simple as long as you know what's going on. The mean effective pressure is a very handy tool to calculate the network output. The only tricky part to this question was realizing how the engine RPM is related to the engine power output. This is a 4-stroke engine, Any four-stroke engine requires 2 revolutions of the crankshaft to complete 1 cycle, meaning that 1800 RPMs is equal to 900 cycles. So all you need to do is multiply the work output of 1 cycle by 900 and then divide that by 60 seconds to find the power output. Okay, so problem 4, we are again looking at a gasoline engine. This engine is running at 2000 RPM. The inlet state is given to us. After combustion, the temperature of air is also given 2000, and we are tasked to find the compression ratio, cycle efficiency, and the exhaust temperature if the highest pressure is 5 megapascals. Now, before we even start, I just want to draw your attention to how we refer to engines in general. For example, here you see that we have a gasoline 4.2 liter engine. Now, 4.2 here refers to the displacement volume of the engine. Generally speaking, when you see a number like this in a car's catalog, for example, 4.2 liters is not the volume or displaced volume of a single cylinder. It is the total displaced volume of the engine, meaning that if, for example, this is a 6-cylinder engine, each cylinder is 0.7 liters. 6 of them will give you 4.2. Okay, so if you're curious about stuff like this, next time you look at your car and you see that it says, oh, 2 liters engine, 4 liters engine, something like that, it is referring to the total displaced volume of your engine, meaning that each cylinder in your engine is contributing equally to that number. Okay, with that aside, let's focus on what's going on. Again, I'm going to, like always, suggest drawing a PV diagram. I'm doing it for every problem here, so you probably know what to expect, but I want you to take this with you through your problem solvings, through your exams, tests, whatever application you're looking at, because it really, really helps you understand what's going on. So this is the PV diagram, and I'm going to actually add the TS diagram as well, just so that we are completely thorough with what we are presenting here. So an isentropic 1 to 2, constant volume 2 to 3, isentropic 3 to 4, and constant volume 4 to 1. So after combustion, remember, combustion happens from 2 to 3. This is where Q in happens. So after combustion refers to point 3. This is the state after combustion. And the problem says that this temperature is 2000. So T3 is 2000 Kelvin. The problem also says the highest pressure is 5 megapascal. It doesn't explicitly tell you what state the pressure is. It just says the highest pressure. This is where the PV diagram comes in handy. If you look at this diagram, you can easily see that point 3 has the highest pressure. So I can claim that P3 is actually the maximum pressure, which is 5 megapascals. So now I know what's going on. At least I know where the data given in the problem fits. So at point 1, I know that P1 is 85 kilopascals, and I know that T1 is 280 Kelvin. I also know that at point 3, P3 maximum pressure is 5 megapascals, and T3, temperature after combustion, is 2000 Kelvin. Let's start with part A, finding the compression ratio. Now, compression ratio is Vmax over Vmin. Looking at the diagram that we have, maximum volume is V1 And minimum volume is V2 or V3. They are the same, exactly like V1 is equal to V4. I can say the compression ratio that I'm looking for is actually specific volume 1 over specific volume 3. Now, again, I want to emphasize there are multiple ways of solving problems of this sort, but I think this is the most straightforward approach. I need to find a specific volume 1 and a specific volume 3. The easiest way of doing it is using the ideal gas equation. Why? Because at both states 1 and 3, I know the pressure and temperature. Ideal gas relates pressure, temperature, and a specific volume together. If I know pressure and temperature, through ideal gas, I can easily find a specific volume. Ideal gas says PV is equal to RT. Keep in mind, the V here is the specific volume, not total volume. So if that is true, which is true, we can use it at state 1, and then we can use it at state 2. So let's start with state 1. So P1 V1 is equal to RT1. P1 is 85. V1 is what we are looking for. R is 0.287, and T1 is 280. Calculator gives you V1 is 0.9454 meters cubed per kilogram. Now let's do the same thing for 0.3, because I know temperature and pressure at 0.3. So P3 V3 is RT3. 5 megapascals. Remember, a few minutes ago, I said that the pressure that you put in the ideal gas equation has to be in kilopascals, while R is in kilojoules per kilogram Kelvin. Now, 5 megapascals is 5,000 kilopascals. So do not forget the units, okay? So 5,000 V3 is 0.287 times the temperature, which is 2,000. Again, use a calculator to get that specific volume 3 is 0.1148, same unit, meters cubed per kilogram. I can easily plug these two numbers back into my compression ratio. V1 is 0.9454, V3 is 0.1148. You get that our compression ratio is 8.23. Now for part B, we are asked to find the efficiency. So the efficiency is 1 minus 1 over R raised to K minus 1. For us, that is 1 minus 1 over 8.23 raised to 0.4. Efficiency is 56.94%. Now, finally, for part C, we are tasked to find the exhaust temperature. Now, this may seem like a new terminology, new word, but it actually is not. If you remember from the lecture, the gas that leaves the cylinder at the end of the process, the exhaust that leaves the cylinder, is the state 4 on our diagram. So the exhaust temperature is actually T4, and we are tasked to find it. The process 3 to 4 is an isentropic expansion. Because it's an isentropic expansion, we can use the isentropic relations. So I can say T4 over T3 is V3 over V4 raised to K minus 1. So T4 is what we are looking for. T3, I already know it's 2000 Kelvin. V3, we just calculated it for part A. And V4, so V4 Again, at first glance, I don't know what V4 is, but consulting the PV diagram, you can easily see that V4 is V1. So 0.9454 raised to k minus 1, which is a very curious equation because what you see in the parentheses here is the invert of compression ratio. So you are actually looking at 1 over r raised to k minus 1, or 1 over 8.23 raised to 0.4. From the efficiency calculation, we know what this right-hand side is. The right-hand side is 0.5694. All that's left to do is find T4 now. So T4 is 1138.8 Kelvin. All right, problem 5. This one is different because unlike the other ones that were focusing on Otto cycle, this is a diesel engine. Now, the inlet conditions are given to us, 95 kilopascals and 300 Kelvin is the condition of air going into the engine. A compression ratio of 20 is also another feature of this engine. Combustion releases 1300 kilojoules per kilogram of heat into the air. Sounds good. Find the temperature after the combustion and the cutoff ratio using cold air properties. Repeating myself, draw the PV diagram. For the diesel cycle, there is a slight difference where the heat addition is happening. So this is the isentropic compression from 1 to 2, but the heat addition phase happens, unlike Otto, happens in a constant pressure process. Then you have the isentropic expansion to 4, and then you have the constant volume heat rejection back to 1. So this is where heat is added, and this is where heat is going out. But now let's see what we know. So at state 1, the intake, P1 is 95 kilopascals, T1 is 300 Kelvin. I also know that the compression ratio R is 20. The compression ratio definition is exactly as before. This is V1 and this is V2, and the compression ratio is the compression of V1 to V2. In the diesel engines, we have a new concept called the cutoff ratio, right? The cutoff ratio, we show it with RC, is the volume of 0.3, state 3, after the combustion, to the volume of state 2 before the combustion. So this is, by definition, we call this the cutoff ratio. And this is one of the things that the problem is asking us to calculate. Okay, back to the data. What else do we know? We also know that the Q of combustion is 1300 kilojoules per kilogram. Okay, so let's start with the first part of the question, the temperature after the combustion. To understand what we need to do, we can take a look at the PV diagram, see where the Q in is happening and where the temperature after the combustion is. The temperature after the combustion is going to be state 3. So in other words, we are looking for T3. Q in, 0.2 and 0.3, they all can be connected to each other through a very simple equation. Q in is Cp T3 minus T2. Now, in Otto cycle, when we were using the Q in equation, we would use Cv because the combustion was a constant volume process. In diesel, as you can see on the screen on the PV diagram, the heat input process is a constant pressure process. So instead of specific heat at constant volume, we are using specific heat at constant pressure. Now, in this equation, Qn I know, Cp I know, T3 is what I'm looking for. The good thing is, I know how to find T2. It's exactly like how we found T2 before for Otto cycle problems. I can relate T2 to T1 through the isentropic compression. So T2 over T1 is V1 over V2 raised to K minus 1. So T2 over 300. Now V1 over V2 is the compression ratio. So you are looking at R raised to 0.4, which is just 20 raised to 0.4. Easily, T2 is 994.34 Kelvin. So now that we have T2, I can plug it here. 1300 is CP is 1.005. T3 I'm looking for, T2 is 994.34. You get that T3 is 2287.87 Kelvin. So I was able to find T3 no problem. The temperature after the combustion is done. Next part of the problem asks us for the cutoff ratio. Let's see what we can do. So the cutoff ratio is V3 over V2. I know that the process 2 to 3 is a constant pressure process, so I can say P2 is equal to P3. I can combine this with the ideal gas equation. Remember, the ideal gas says P is RT over specific volume. So if I combine these, I can say RT2 over V2 is equal to RT3 over V3, right? I'm just combining these two equations. Obviously, I can cross R's and play with this equation a little bit. See, I'm looking for V3 over V2. I can say V3 over V2 is T3 over T2. Look at that. So yes, cutoff ratio is defined as the ratio of two volumes, but because ideal gas equation is true and because 2 to 3 is constant pressure, I can relate the cutoff ratio directly to temperatures. So I can say cutoff ratio is exactly T3 over T2, both of which I know the numbers for. Cutoff ratio is T3, we calculated it a few minutes ago, 2287.87, divided by T2, again calculated earlier, 994.34. Plug in your calculator, cutoff ratio is 2.3. So this is how you tackle a diesel engine problem. It has a few more players than the Otto cycle. It has the cutoff ratio thing, which potentially can throw you off guard. But just remember the lecture, just remember your equation sheet, and just know that the cutoff ratio is the ratio of volume 3 to volume 2, and you can easily relate it to temperature 3 and temperature 2. All right, problem 6, our final problem for this video. We are again dealing with a diesel engine. The compression ratio is given 20. The inlet temperature is also given. The maximum pressure of the cycle, very good, that is given too. Maximum temperature of the cycle, also given. We are tasked with cold air properties to find the cutoff ratio, the expansion ratio. This is ratio. That's a typo there. And the exhaust temperature. So let's see what we can do. I'm going to draw the PV and TS diagrams, like always, just so that I know what I'm doing. Point 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Now, you don't need to be pretty accurate with the diagram. As long as it shows you the correct process, you're good. I'm also adding TS diagram here because the problem is talking about maximum temperature, and maximum temperature is not something that I can see on PV diagram. So, a TS diagram. I have an isentropic 1 to 2, constant pressure 2 to 3, isentropic 3 to 4, constant volume 4 to 1. So this is 1, 2, 3, 4, back to 1. The maximum pressure is 6,300. Looking at the PV diagram, you can conclude that P2 equals P3 is the maximum pressure for this cycle. For the maximum temperature, looking at the TS diagram, you can clearly see that T3 is your maximum temperature. And the problem says it is 1800 Kelvin. So I was able to label the maximum pressure and maximum temperature with state numbers. P2 and P3 are 6,300 kilopascals, and T3 is 1800. Now let's write down the rest of the provided data. At point 1, I know that temperature 1 is 290. I also know that the compression ratio is 20. And that's all I know. Let's see what we can do. Starting with part A. Now, cutoff ratio from previous problem, we know that RC is V3 over V2, or as we showed in the previous problem, it is T3 over T2. Now, the good thing is, I know what T3 is. It is 1800. T2, again, initially, I don't know, but you guys are pros by now. You know how to find T2, so let's do it. Easily relate T2 to T1 through the isentropic process. T2 to T1 is going to be V1 to V2 raised to K minus 1. So T2 over 290 Kelvin, this is Kelvin, is equal to, now V1 to V2 is the compression ratio. So R raised to K minus 1. For us, that is 20 raised to 0.4. T2 is going to be 961.19 Kelvin. Now that we have T2, we can go back to our equation here. Cutoff ratio is 1800 over 961.19. Using a calculator, RC is about 1.87. For part B, the problem is asking for the expansion ratio. Now, expansion ratio is not a common defined expression that we had in the lecture before. It is something unique to this problem wording. You may see it here and there in different textbooks, but is not a standard expression. However, that shouldn't be too difficult for us because the problem is giving us the equation for this expansion ratio. It is volume 4 to volume 3. So all we need to do is find the ratio of V4 to V3. Let's see if we can do it. So this one is a very interesting question, V4 to V3. What do we know about them? Now, what I know is that first V4 is equal to V1 from this diagram here. I also know that volume 3 over volume 2 is the cutoff ratio. So I can make the argument that volume 3 is cutoff ratio times volume 2. Now, the reason I'm playing with these equations is very simple, actually. The ratio of V4 over V3 can now be expressed as V1 over RC V2. Now, V1 over V2 is the compression ratio of the engine. We talked about it before. So this is actually compression ratio over the cutoff ratio. So your expansion ratio, V4 over V3, is going to be 20 over 1.87. I forgot to calculate this using a calculator, but I can trust you with this little calculation. Now, finally, for part C, we are tasked to find the exhaust temperature. Again, as we discussed in the problem 4, the exhaust temperature is the temperature of the outlet, right? And that is what we are going to find. The relation between temperature 4 and temperature 3 follows the equation of an isentropic process. I can say T4 over T3 is volume 3 over volume 4 raised to K minus 1. Following what we know above, I can replace V3 by RC V2 and replace V4 by V1. And this is exactly the invert of the expansion ratio. So you are looking at RC over R raised to K minus 1. For us, that is 1.87 over 20 raised to 0.4. All is left to do is plug in numbers. Remember, T3 is 1800. And now T4 is 697.58 Kelvin. And so this is our exhaust temperature. Now, the question is not asking it, but let's say we are interested in finding the efficiency for this engine as well. So the equation for the efficiency of a diesel engine is very similar to that of the Otto cycle with a little bit of modification. The efficiency is 1 minus 1 over R raised to K minus 1. This part is the same, times, this is where the modification comes in, times cutoff ratio raised to K minus 1 divided by K times cutoff ratio minus 1. So in this problem, if we are interested, then the efficiency is going to be 1 minus 1 over 20 raised to 0.4 times 1.87 raised to 1.4 minus 1 over 1.4 times 1.87 minus 1. Again, I have not done the calculation on a calculator, but I can trust you with doing the numbers and getting an efficiency for this engine. So this was the last problem for this video. Now, are these problems the only type of problems that you can see from this topic? Absolutely not. Is the approach to Otto and diesel cycle problems the same as these? Yes, the approach is going to be the same. If you are comfortable with these problems, you should be comfortable with any other problem from this discussion. Thank you for sticking to the end and watching this video, and I will see you in the next one.